In his original email to me in March, Phil advertised this as an informal workshop. The quality of the presentations that I've seen so far, I'm afraid I missed yesterday afternoon, but I was here for the morning. It's been rather intimidating. This is going to lower the standard, I think. I also forgot what my original title was. This was going to be on disk wins, but as I was working on the talk in the last few days, I thought I really want to make a closer connection to planets. And I wish I had chosen this even vaguer title, which gives me that liberty. Anyway, I'm going to stick to the original billing and be somewhat informal. So in fact, before I talk about wins, I was going to say a bit about that. Let me just skip forward to something that, okay, well, this is here just for fun. This is on the top, a very early theory of planet formation. And on the bottom, a comment on the value of the enterprise. Anyway, moving on. So I think we were all struck by these images when they first came out. The one on the left, I think in 2014, with absolutely no supporting technical information whatsoever. And speaking for myself, my first reaction was, good grief, it looks like a theorist's dream of a circularly symmetric, apart from inclination effects, planet. It's too good to be true. And then, of course, one looks at the rings there, the gaps, and wonders, could those be planets? And now we have even more striking images from D#. So we've heard already at this conference, and of course there's been much ink shed before this conference, on the hypothesis that these gaps are formed by planets. Now, if that's true, never mind that, it's very important because the subject here is, after all, the challenges of understanding planet formation. And this would be, I think, I don't form planets myself, but would be a very powerful constraint on the theory. So it seems to me that there are at least two challenges presented by these rings, especially the ones at the largest radii of order 100 AU. There's a mass problem, as the previous speaker mentioned. I mean, I haven't made the estimates for the masses myself. I rely on the analysis in one of the D# papers, the 7th in the series. And if you look through their table, which constructed from simulations varying the disk viscosity, varying the Stokes number of the particles, and so forth, varying the surface density of the disk, as a rule, might be one exception, the inferred planet masses responsible for the outer rings, never mind how many gaps one planet can produce, are in this difficult range. They're sub-Jovian, but they're more than 10 Earth masses. And I thought we didn't know how to form such objects in a young disk which still has lots of gas in it. Now, of course, in our solar system, we do have Uranus and Neptune, and they have, at least in the case of Neptune, I think something like 10% of the mass in hydrogen and helium, a total mass of 17, which is well above the supposed critical core mass. Hilke will probably explain to me at coffee how those things form. But they might have formed later, I suppose, when the disk was depleted. These disks are still quite healthy. So there's a problem with mass. And there may also be a problem with timescale. Certainly the old theory of core accretion from the 1980s would be totally incapable of explaining a core mass this large at such an early time. They were at pains to explain the formation of Jupiter and Saturn's cores in the minimum mass solar nebulae. It's considerably smaller radii where the timescales are shorter. Since then, we've had pebble accretion and other innovations, concentration by, as Kathy said and the previous speaker said, in features produced by spiral arms and so forth. So perhaps there is a way, but certainly, come back to my original point, this would be a very important constraint. So given the the potential importance of this as a constraint, I think it behooves us to consider whether there might be some other explanation. Okay. Now, I'm not going to try to sell you on any particular explanation, but I went through the literature rather hastily, and I'm sure I missed some possibilities. But this is at least a partial list of mechanisms for forming rings and gaps in disks without benefit of planet. Okay, and it goes on for a second page. And if one of your favorites is omitted from this list, please correct me later. But already, and I'm not saying that these are equally plausible, but they have their own strengths and weaknesses, and there's some that I prefer over others. But in the sheer numbers here, we're almost comparable to the Democratic presidential nomination. I didn't quite reach 21 or whatever the current count is, but some of these could probably be split into this. Okay. I think one of the main points is we know that turbulent systems that are vertically thin, like planetary atmospheres, have a tendency to self-organize on scales larger than the atmospheric scale height. If there's any power at all that gets up onto those scales, it tends to give us things like zonal flows, large-scale weather patterns on the Earth, and whatnot. Now, we understand that in systems like planetary atmospheres and more artificial ones where there is may or may not be rotation, but there's relatively modest shear. I don't think we understand it so well in a disk. And so there's work to be done there theoretically. And also, I should say that maybe in defense of some of these models, in some cases, the authors set out to produce or to exhibit a ring-forming mechanism. But in most of these cases, they just stumbled across it. Okay, they didn't have a hidden agenda, and yet they found these things. Now, at a conference a year ago that Hilke organized in Berlin, I was talking, I think it was to Ted Bergen, and he had talked a bit about these gaps and rings and some CO line observations from which he thought one could, solidify the case for the existence of a planet. And I complained along these lines with a subset of these mechanisms. And his objection as an observer was, well, those aren't computable. And, on the one hand, that seems like an unfair comment because, you're not allowed to assume, draw such a strong conclusion as the existence of a planet without, a lack of alternatives. But on the other hand, I thought it was a fair criticism to the theoretical community by the observers. They have these beautiful data, obtained a great effort, and we can't tell them exactly how to fit one of these other mechanisms or any of these mechanisms to those gaps and rings. We can do it for a planet because, with all due respect to the people who make these models, there are some uncertainties and challenges, computational challenges. It's a relatively straightforward process. There's a strong underlying theory and so on. But for these, there isn't. Okay, so that's my polemic, my harangue there. Let me move back and say a little bit about winds. Okay. My roots are in dynamics. I'm originally stellar dynamics and then hydrodynamics and MHD. I got interested in accretion disks. What really, I think, drew me strongly to protoplanets was this work a few years ago on low vibrational CO emission from 60-odd Titari stars, observed at a resolution, a velocity resolution of 3 kilometers a second. So these lines are roughly 10 times that wide at the base, so they're well resolved. The remarkable thing about them for a dynamicist is that while some of them look like what you might expect from the surface of the disk, they're double peaked. Many of them are just single peaked. So what's going on there? Maybe you might think it was emission from very far out in the disk, filling in the line. But the authors argue against that for, I think, good reasons, and one could deduce more reasons. So their interpretation was that it was a slow sub-Keplerian wind off the disk. By the way, the excitation temperatures of these lines are a few thousand degrees. But it's almost certainly not collisional excitation. It's probably infrared pumping. And even then, it's very hard to understand the strengths of these lines. They are really quite luminous when you consider the energy available from the stellar continuum to pump them. It's just barely possible. All right, so this is telling us something about wind outflow. It's not planets, just winds, but there's a connection in my mind. So Lila, my former PhD student who's now here, for his thesis, did computations of both photoevaporative winds, purely photoevaporative winds, purely hydrodynamic ones, propelled by hard radiation shortward of the Wien peak of the from the protostar. We didn't consider external photoevaporation, although I acknowledge that's important. And also MHD winds. I don't have time to go through all the details, but let me just make a few broad points, things we've concluded, and things that remain to be done. That relate to planets. So first of all, the microphysics, the heating and the cooling processes, magnetic fields, I count that as microphysics, tensorial conductivities that affect how the fields couple to the gas, and the chemistry and the dust. Dust is always an issue, are all very important. Now, I'm not saying that we got it all right. As Kathy mentioned yesterday, there's still an ongoing discussion as to which part of the stellar hard radiation is most responsible for the purely photoevaporative winds. But there's no doubt that this stuff's important because one can see in one's model that as one turns things on and off, it makes a difference to many aspects of the wind. Most of you probably care only about the overall mass loss rate because that is important for the evolution of the system and the time it has available to form planets, but also for other aspects like whether the wind is molecular or atomic, for example. Now, photoevaporation will surely occur at some level because we see this hard radiation. It will drive mass loss. On the other hand, these disks secrete. We observe that, and we don't really have any good, in my opinion, way of explaining the accretion process that doesn't involve a magnetic field somehow, even if that's MRI turbulence in the disk. And given how non-ideal these systems are, given all that microphysics, the poor coupling, it seems at the moment, although one might wonder if this will hold up, that you can't even make MRI work without a large-scale mean field. These systems don't easily make their own dynamo because they're so resistive and amipolar and Hallish and so forth. So if you put a mean field into a system that already has a photoevaporative wind, you get a magnetized wind. And that means that you now couple it, and because it's magnetized, there's the bending of the field lines by the inertia of escaping material creates a magnetic torque on the surface of the disk, which removes angular momentum from it and drives some level of accretion. So once you introduce the magnetic field, there is a connection between outflow and inflow. Here one can distinguish perhaps two versions of magnetic winds. The original Blandford and Payne type, magnetocentrifugal. In their original model, the disk was dead cold. It was just a zero thickness layer. So this is the limit where the magnetic energy density is large compared to the thermal energy density, and the lines don't bend easily. The Alfvén radius is a large multiple of the radius at the foot point of the field line where it attaches to the disk. Now, the trouble with those models as applied to protostellar disks is that if you look back at not the successors to Blandford and Payne, which did put in a finite thickness and a finite temperature for the gas by people like Koenigsegg and Wardle and Pudritz and many others in the early 90s, they typically give inflow speeds that are about of the order of the sound speed, much faster than viscous. And so I admired those papers, but I thought that they were not relevant to planet-forming disks because we measure the accretion rate, and if you put in an inflow speed, given the accretion rate, 10 to the minus 8 solar masses per year or so, and in the inflow speed of order of the sound speed, which is about a kilometer a second, you can calculate what surface density is needed at one unit. It works out to be less than 1/10 of a gram per square centimeter. 10 to the 4 orders of magnitude less than the minimum mass solar nebula. This is no place to form planets, right? So briefly, and Juaning can probably tell you a lot more about it, the current view is that even if the accretion is driven by winds, and I think there's plenty of theoretical evidence in favor of that. MRI doesn't seem to quite work in these non-ideal situations. The wind is only coupled to the upper surface of the disk, to a layer that has a column of order 10 to the 22 hydrogens per square centimeter, or something like, vastly less than the full column of the disk. And that material does move in very fast, but it's only a fraction of the column, and the rest of the disk is accreting very, very slowly, if at all. The propulsion of the wind is largely magnetic, although partly thermal, because we still have those hard photons. But it's not really centrifugal. It's more that the poloidal field that you put in gets wound up into an azimuthal field, and then the pressure gradient of the gradient of the magnetic pressure associated with that is what really pushes the material off. So that latter type differ in some respects from the old ones. They're compatible with high column densities. They're slower than magnetocentrifugal ones, and they're more molecular. Okay. My final point, and this is really more of something on my to-do list. I don't know if I'll get to it before I retire, but I think we need to take seriously, if the accretion really is driven by winds, and I won't say more to defend that, but I think it's reasonable, then we may have to rethink a lot of the past work on the interaction between planets, and because planets do sometimes exist, and the gaps they open, and how they migrate, and how they accrete, okay? We've been thinking, all of that work, almost all of that work, has been phrased in terms of a disk viscosity, which is very convenient. It's local. You can describe it by one parameter. It doesn't mean it's right, okay? And if you put, okay, well, enough on that subject. Skipping. All right, so now I want to say something about transition disks. But even before those lovely rings were seen, there was evidence for large cavities in the inner parts of protostellar disks. And recently there's been speculation that the existence of those cavities may be essential for the formation of, I'm thinking of the work by Li and Chang here, the super Earths that have very tenuous atmospheres. But they maybe not. But in any case, many people have assumed that these cavities are created by planets. Now, I should say that these cavities often extend, well, let me back up. Their existence was originally recognized cleverly and indirectly, not by their being directly resolved, but rather from the spectral energy distributions of class 2 systems, T-Tauri stars, which showed a dip at around 10 microns, 8 to 20 or something. That dip was interpreted as indicating a gap or a cavity in the dust, at least, extending out to a few to many tens of AU. And now that we have ALMA, and before that the SMA, and other instruments in the infrared, we can actually directly resolve some of these cavities, and indeed they're there. And the inference is that the dust in those cavities has to be suppressed by a factor often of something like 10 to the 4 or more in order to explain those dips. Nevertheless, the cavities aren't totally free of dust in some cases, because we often see a 10 micron silicate feature. So the fact that it's at 10 microns means the dust has to be, around the temperature in this room, more or less. So we're talking about AU-ish distances. There's some material in there. And also, looking at optical or wavelengths or near UV wavelengths with HST, we can see scattered light. So, but in the submillimeter, the mid-infrared, and so on, there seems to be very little dust, very little submicron dust. How much gas there is in these gaps is very unclear. There have been only a very few studies since ALMA came online of this, and they rely on tracers like carbon monoxide or its various isotopologues, or HCO+, because the molecular hydrogen itself is not directly visible except possibly in fluorescence from ultraviolet. A little work on that. And we don't know, or at least there's a controversy over the abundance of these species relative to hydrogen. It could be quite different from what we see in the interstellar medium. But the balance of the evidence suggests there's at least some suppression of the gas in the gaps by something anywhere from a factor of a few to a few orders of magnitude. Maybe not. The gas gaps, the radii of the cavities in the gas seem to be somewhat smaller than that of the dust. And the gaps in the submillimeter in at least one or two well-studied cases are slightly larger than the gaps in the smaller dust that's responsible for the 10 micron emission. All right, so okay, so if this is planets, they could perhaps open up, if they can prevent if they're massive enough that they can prevent material from crossing their orbits, they can perhaps open up such a gap. But a wrinkle, a further difficulty is that a great many of these transition disks are still accreting. It looks like, on average, somewhat more slowly than full disks lacking large cavities, but that's not entirely clear. James Owen has suggested there are two populations of these transition disks, ones that have smallish gaps, less than a few AU, and are essentially no accretion, and others that have the large gaps, bigger than 10 AU, and more massive outer parts, actually. These are often the brightest submillimeter sources. Maybe slightly more massive, more massive hosts, which really just means a solar mass or so. And those are the ones that still accrete at essentially unreduced rates, maybe 10 to the minus 8. So you have to be, if we don't distinguish those populations, there's a danger of inferring a reduction in the accretion rate for the whole population, for what is really an average between two populations. Anyway, so how does that work? So even if a planet opens up a gap, how does it get material all the way down into the star? Well, there are sort of two possibilities. One, it's just an ordinary viscous accretion. The gas has, so there's a lot of gas in the disk, in the cavity, but we just don't see it in the infrared because the submicron dust has been completely stripped out by a pressure rump created by the planet. Quantitatively, it's very hard to make this work because the Stokes numbers of the small grains that would emit at 10 microns are just very difficult, are small enough that it's very difficult to imagine filtering them out completely. The other possibility is that the material is, maybe in combination with the first, the material is moving radially much faster than viscously. And then you need a lower surface density. So it was at this point in our thinking that Lila and I realized that perhaps those old wind models are just what you need. So yes, we've had this. Right. So I think I'm going to finish. Well, I wanted to show some conclusion slides, but just finish with this point. So our first paper together, we made this suggestion, which has been, I would say, not particularly enthusiastically received, but nevertheless, I've got you as a captive audience, so I'm going to reiterate the point. Okay. The speed of viscous accretion goes like alpha, some number less than 1, which for MRI accretion would be, roughly speaking, the ratio of the magnetic energy density, or more precisely the magnetic stress, to the thermal pressure or energy density. So a number, in that case, which needs to be substantially less than 1 by at least a factor of several, or maybe 100 or whatever, because if the stress gets too strong compared to the thermal pressure, MRI shuts itself off. And that's even more true when you've got a lot of ambipolar diffusion. All right, so alpha small. And then you have this factor of H over R that comes out naturally. if you say that the viscosity is alpha times the square of the sound speed, or say alpha times the sound speed times the thickness. And then you have the sound speed. So these two factors in front are probably in combination smaller than 1 over 300 or something, optimistically. But with winds, take off these two small factors. So let me start. So first of all, alpha, the analog of alpha, the ratio of magnetic to thermal stress, could be of order unity because it's not an instability. It doesn't have to shut itself off. Okay, so that could be one. And this factor goes away because at the same magnetic stress level, winds are much more efficient at removing angular momentum from the accreting material simply because the stress is exerted on the surface of the disk rather than across its thickness. Okay. So that's why these models naturally produce accretion speeds of order, because the old models were strongly magnetized and coupled right down to the midplane, give you this speed of order the sound speed. Okay. So anyway, so just to close on that argument, if you then put in a radial speed of a sound speed, one sound speed, and then you allow it to scale with radius as it would in the minimum mass solar nebula, this is the surface density you get, as I said already. About 4 and a bit orders of magnitude less than the minimum mass solar nebula, at least at 1 AU. So you might not even have to reduce the dust fraction. Okay, so that was just a pet idea of mine that I wanted to push. But in the spirit of an informal workshop, I wanted to talk just briefly about what my views about what needs to be done next. So there's an observational agenda, but we're not observers. Okay, but let me just call out the first bullet. If these things are really planets in the outer gap, so it will be very important for us. So what can be done observationally to confirm that? The most obvious thing, it seems to me, is to go to higher signal-to-noise ratio and higher resolution. The D-sharp images were used integration times per disk of less than an hour. And they were in band 6 at 1.25 millimeters, because they weren't allowed to go to higher frequency at that time. So Sean Williams tells me that now, at least for selected systems, they could repropose and go to longer exposures, maybe in band 7 at 345 gigahertz, 33% smaller wavelength, get higher resolution. Why do that? Well, if there are planets in those gaps and rings, then at some level there has to be some non-axis symmetry, because the planet opens the gap, of course, as we all know, by exerting torques on the edges of the disk. And those require non-axis symmetric parts of the potential. So let's look for them. And then there are these other things which I'll skip over. What about the theoretical agenda? Well, many things need to be done, but just those things that relate, it seems to me, to what I told you just now are these three. I think that long list of mechanisms for forming rings and gaps without planets, none of those mechanisms, to my knowledge, has been very thoroughly explored and quantified. There are issues of box size, if they're found with shearing box simulations. There are some of them require bits of physics like heating and cooling by the central star or whatever that not everybody puts in. Some of them are quite challenging computationally because, as I said, when one is looking for self-organization on scales larger than the disk thickness, but on the other hand, that may be due to the spillover of turbulent power, MRI or whatever, on scales small compared to the disk thickness, so you need to resolve a large range of scales. And you probably have to integrate for a very long time because some of these things are very slowly developing. And I should just say that these processes are not necessarily related to whatever it is directly, to whatever it is that drives accretion. So you shouldn't just reject these, even the hydrodynamic mechanisms, because you think they can't explain accretion. They may not be able to, but they may still be able to produce rings. Okay, and then of course, there's this problem. Can we form sub-Jovian planets, or maybe at these large radii very quickly? or maybe form them at smaller radii and have them migrate out. That's going to be a long road, I suspect, but obviously, if we confirm that there are planets there, this will become urgent. And maybe less important than the other two, but I'm fond of winds, and I think this is a clearly understudied area. What happens if we can't rely on viscosity to make the disk spread? It's just moving inward because of a wind torque. How does that affect the rate at which planets accrete material, the rates at which they migrate, the sizes of the gaps, and all that? Unfortunately, that's going to be hard because it's an intrinsically three-dimensional problem. You can't ignore the azimuthal dependence because you have a planet here and other azimuths, and you can't ignore the vertical direction because after all, you've got a wind there. So that may take some time. All right.
Maybe a couple of questions, comment?
Not really a question, but I do hope you stick around to the absolute last talk on Wednesday because it's entirely about your last point.
Okay, thank you. I look forward to it. No?
So a bit of a general question is the wind-driven disks, and the axisymmetry. I mean, do we have a problem theoretically keeping these disks axisymmetric? In terms of, so it's hard to kill spiral waves, but if you just consider disks of very low turbulence, if a planet starts to open up a gap, you get all kinds of vortices that may be very long-lived if you just say, well, the viscosity is terribly low. I wonder what your opinion is on that.
Well, even quite apart from winds, this is one of the reasons I think that I said we don't understand self-organization in disks as well as we do in things like planetary atmospheres. There is a very strong background shear. And so any slow process of rearrangement of material tends to become axisymmetric just because of that. Now, I recognize that long-lived vortices are a possible exception. But theoretically, and I've spent some time thinking about it, it's difficult to understand how vortices whose radial thickness is larger than the vertical scale height, and hence which are supersonic with respect to the Eckern flow, can survive very long, notwithstanding the fact that one sees them in simulations. I think there's an absence of supporting theory, by which I don't mean numerical simulation, to understand those things. But yes, I had some slide on that I took out. I think it's an interesting question. But again, there's an overall tendency for the strong background shear to make any sort of slow ring-forming process become axisymmetric.
I think I must just list something, because surely if you're accreting at a sonic rate, your disk lifetimes are going to be incredibly short then.
Oh, I'm sorry, I didn't explain the picture fully, and I should have drawn a cartoon. These systems have a very healthy outer disk, as observed. They're actually quite massive. So the idea is that out there, beyond wherever the outer cavity radius is, you have a full disk, which is coupled to the wind only in its surface layers, and has a large reservoir of mass, and then that flows off into the gap, and in the cavity, the whole thing is magnetized, and you just have this very low surface density.